Okay, good morning, folks. I've got 1 minute past. It looks like everybody's online today. Nice to see you. I hope everything is going well and everyone is nice and safe. Are there any questions or concerns before we get started for today?
I don't think so.
Okay, great. If not, then let me switch to sharing screen. Okay. Okay, so thus far, we've been tying together several of the threads that we've been continuing for the past several weeks. Last time we discussed the Lagrangian and the Hamiltonian of electromagnetism. That was not covered by the discussion we had had previously because of the velocity-dependent magnetic force. And we talked about how to construct a Lagrangian of this type by minimal coupling, which was loosely P goes to P minus, let's say, Q over CA. And this led to a discussion of gauge symmetry and gauge invariance. Since physics doesn't depend on your choice of the vector potential or the scalar potential, it only depends on the electric and magnetic fields. That introduces a nice continuous symmetry for how you can transform your gauge fields without affecting physics. And that was a nice lever to discuss the standard model of particle physics. Since the gauge symmetry that one chooses uniquely determines the form of the Lagrangian that gives you the equations of motion. We spent considerable time discussing classical versus quantum, the classical expectations versus the experimental facts. One of those was wave-particle duality. As seen both by the photoelectric effect and electron diffraction. We talked about clearly non-commuting observables in quantum mechanics. Which I think the clearest example is probably the Stern-Gerlach effect. And so this led us to introduce a wave function, a psi of x, which we know can be interpreted as an infinite dimensional vector psi projected onto a basis in coordinate space, x. And we said the wave function is essentially a probability amplitude and that the wave function squared, psi squared, which is essentially the intensity of the wave that gives you the probability density. We talked about how experimental facts force us to reckon with the notion that there is a wave that exists at the level of one particle, not just as a bunch or a beam as some collective effect. And let me remind you of a few of the important features of the Poisson bracket algebra because we are going to use them today, hopefully for the last time. So we said the Poisson brackets provide a way algebraically to define what you mean by conjugate momentum, because all momenta have a bracket that is 0, all coordinates have a bracket that is 0, and a coordinate and a momentum have a bracket that is non-zero only if they are canonically conjugate pairs, if I equals j. And we saw that it was possible to express the equation of motion, the time dependence for any observable omega, by taking its Poisson bracket with the Hamiltonian. And in terms of this discussion of symmetry, we saw that the Poisson bracket also provides a way to generate a generic symmetry transformation, not just the time evolution given by the Hamiltonian. And so we said under a general symmetry transformation, omega maps to, excuse me, something that looks like a nested set of Poisson brackets, e to the fill in the blank bracket with a generator g times a parameter a on the original observable omega. This was about as far as we could take it in classical mechanics. In quantum mechanics, where that becomes a commutator, we'll find a much more compact and convenient way to express this. Okay. So without further ado, let's discuss canonical quantization and derive the Schrodinger equation from this. So quantum mechanics is, of course, a very different language than classical mechanics, but the argument is that the way that symmetries, energy, momentum, all of these core concepts that we build in classical mechanics, the way that those behave must be the same in quantum mechanics. So in my mind, quantum mechanics is the leap of faith beyond classical mechanics, because up until now, all of our intuition has been built on balls rolling down ramps or hockey pucks colliding with each other. But in quantum mechanics, only the abstract concepts of energy and momentum make sense anymore. Quantum mechanics follows an intuition of its own, but it's quite at odds with our everyday intuition, and it just takes a lot of experience before that becomes natural to you. But the point is that the way in which these concepts of energy and momentum operate is defined by their algebra, and that's directly connected with the symmetries. So because quantum mechanics must encompass classical mechanics, it must reduce back to the classical limit in the limit h bar goes to 0, which we'll discuss momentarily. Reduce back to classical mechanics. The algebra of these symmetries must still work the same way. Otherwise, it would be impossible to recover classical mechanics as some appropriate limit of quantum mechanics. So, so this was based on symmetries, and specifically the Lie algebras of those symmetries. So if quantum mechanics is an effective theory of nature, or classical mechanics, I should say, is an effective theory of nature, effective theory or an approximation of the true quote-unquote quantum theory in the limit where wave-particle duality cannot be resolved. We discussed that characteristic scale of being able to resolve wave-particle duality or not is described by the constant h bar. So h bar going to 0 is the classical limit. Of course, h bar is a constant of nature. It's not a variable that I can just take to 0 because I want to. What I really mean is that when you are operating at scales so large compared to h bar that h bar is effectively 0, then you are in the classical limit. So for instance, we have position times coordinate much greater than h bar. So that h bar is the units of any coordinate times its canonical conjugate. So this would be, for instance, measuring a quantum system on distances much larger than h bar over p, and up to a factor of 2 pi, this is its de Broglie wavelength. So if there is a characteristic wavelength, but you measure it over much longer distances, you don't need that wavelength. It might as well be zero. Similarly, you can have angular momentum much greater than h bar. H bar is the unit of angular momentum. So a system with large angular momentum is classical. There's one other that I wanted to mention here, which is a density. If I take this statement about position and momentum, x times px, y times py, z times pz, this should be much greater than h bar cubed to be classical. The volume x times y times z then gets multiplied by the factor of momenta, px, py, pz. If I divide everything across to the other side, then I have right. So if I divide the momenta to the other side, I have volume much greater than h bar over px, h bar over py, h bar over pz. And this number on the right-hand side is basically three factors of the de Broglie wavelength, x, y, and z. I guess they could be different depending on how big your momenta are. So this is expressible in terms of the density. If I divide everything through to the other side, then 1 over lambda cubed should be much greater than 1 over the volume. And that 1 over the volume is the number density. So these kind of things are criteria for when a classical limit will apply, a limit of large angular momentum, long distances, and that long distance is also related to densities that are low enough that you are not squeezing particles together so closely that their de Broglie wavelengths begin to overlap. So this would be a quantum density. I guess this one is the quantum density. So all of this is to say that since quantum mechanics must reproduce classical mechanics or h bar goes to 0, it must be some representation of the same underlying algebra. And so that means that there should be some kind of map that we can make between a classical Poisson bracket and a quantum commutator. So that map, which is due to Dirac, is that the Poisson bracket of any two quantities A and B, which are just functions in classical mechanics, gets replaced with 1 over I h bar times the commutator of two operators in quantum mechanics, A and B. So this gives us a prescription for maintaining canonical pairs across quantization. If canonical pairs of variables are defined such that their Poisson bracket of Q with P is a Kronecker delta Ij, then the quantum version will tell me that the commutator of my coordinates and the corresponding momentum should be IH bar delta Ij. So, and this is consistent with what we had discussed earlier on in the semester when we talked about the translation operator on functions, that the position operator and the wave number operator, which is related to h by h bar to the momentum, had a commutation relation given by IH bar. So in general, in classical mechanics, all of our observables, omega are functions of the coordinates and the momenta. And when we turn these into quantum Hermitian operators, this will become an operator function of the corresponding position and momentum operator. So what I mean by this is that if I have, for instance, classically a Hamiltonian for the harmonic oscillator, which is p squared over 2m plus 1/2 kx squared, then in quantum mechanics, I will write this as a Hamiltonian operator. This is the momentum operator squared plus 1/2 k times the coordinate operator squared. So the goal is to sort of replace one-to-one the variable with its operator version. However, this is not always possible. So canonical quantization is a general procedure that works in most cases, but it is not foolproof. So one inherent limitation is that, of course, in classical mechanics where P and Q and all of the omegas are functions, they commute with each other. So I can write factors in any order. So classically, AB equals BA. But in quantum mechanics, these things are different. AB is not necessarily the same thing as BA. So if I have a classical theory that multiplies some things together, I don't know automatically which one to write down when I go to a quantum theory. As long as I don't have too many factors being multiplied together, there is a best practice, which is to take the symmetric form. Symmetrized form, where it's basically half of column A plus half of column B. So what I mean by this is, for example, when we talked about the Hamiltonian of electromagnetism, we said that this can be written as P minus Q over CA squared over 2M plus Q phi. And this is an example of a term, or this contains an example of a term where the ordering is ambiguous. So if I open up the parentheses, this is my ordinary kinetic momentum P squared over 2M minus, so I get a factor of 2 minus Q over MC P times A plus Q squared over 2MC squared A squared plus Q phi. So if I want to quantize this Hamiltonian, the kinetic momentum is easy. The parts that are perfect squares are fine. Both of my potentials are going to become operators, but the part that I don't know what to do with is this P times A, because in general, P and A will not commute with each other. So the symmetric form would be minus Q over MC, and you choose PA with the factor of 1/2 plus AP, and with a factor of 1/2. So the symmetric prescription is nice because it ensures that this form will be Hermitian. Equals H dagger. So recall that even if P is Hermitian and A is Hermitian, the product P times A is not automatically Hermitian. And only if you symmetrize it, for instance, that if you have them in both orders, do you guarantee that the whole thing will be Hermitian. So this works, and I think this will be more than sufficient for our needs for the rest of this class. But again, this is not perfect. This is known to fail for polynomials of high enough degree. So this is the prescription of canonical quantization. And the really interesting part now is when we apply this to the equation of motion. So the equation of motion given in Poisson brackets in classical mechanics are essentially Hamilton's equations. The rate of change of any observable with time is given by its Poisson brackets with the Hamiltonian. So if I apply canonical quantization to this formula, I obtain Heisenberg's equation of motion. multiply both sides by a factor of h bar, and then I can turn the Poisson bracket into a commutator. So this is d omega operator dt equals commutator of omega operator with the Hamiltonian operator. And it may not be immediately obvious, but this equation is completely equivalent to the Schrodinger equation. We will show that next. One should also mention what kind of picture of quantum mechanics we're using when we write down something like this. Because in order to write this down, I have time dependence, d dt of an operator. So this picture of quantum mechanics is called the Heisenberg picture. In this formulation, the operators are time dependent. The observables are time dependent. So I will have x of t, I will have p of t, and for general observable omega, which is built out of x and p, this is also a function of time, x of t, p of t. And this makes sense to correspond to classical mechanics, because in classical mechanics, we had these as just variables that are functions of time, x of t, p of t, omega of x of t, and p of t. Heisenberg picture is not necessarily the most intuitive way to formulate quantum mechanics, so we will quickly switch out of it into something more standard. But Heisenberg picture is the one where the correspondence to classical mechanics is the most transparent. So we've written down the equation of motion in terms of a commutator with the Hamiltonian. We also know how to write down the formal solution to this because we also already solved it in classical mechanics. Solution to the equations of motion. In the classical setup, where we had d omega dt equals Poisson bracket of omega with the Hamiltonian, we found the formal solution, which was that omega of t is what you get by exponentiating this operation. E to the Poisson bracket of whatever you want with the Hamiltonian times time, acting on omega at t equals 0. And for simplicity, I'm just going to call this omega naught. In classical mechanics, that was the best we could do. We can write down something equivalent for quantum mechanics under canonical quantization. So the formal solution is d omega hat dt I h bar equals Poisson bracket of omega with the Hamiltonian, with formal solution omega of t equals e to the minus I over h bar, commutator of fill in the blank with the Hamiltonian operator times time, times omega naught the operator. So let's simplify this expression a little bit. To see what happens, it's easiest again to go back to the case of an infinitesimal transformation. So consider a small step, t goes to epsilon of time evolution. And then we can unfold what this is a little bit more. So omega of epsilon is the identity operator minus I over h bar, commutator of fill in the blank with the Hamiltonian times epsilon plus corrections of order epsilon squared acting on omega naught. So if I let this operator apply to omega naught, I just get omega naught minus I over h bar, and the commutator is omega naught times h minus h times omega naught times epsilon. And again, the corrections are order epsilon squared. Now, since these are operators that I can write in either order to the left or to the right, I see that this form, 1 plus something times epsilon, it looks like I had omega naught and I put h to the right of it, right side of omega naught. And on the other side, or in the second term, I put it in the other order. So to within the accuracy of this small translation, this is equivalent to saying this is 1 minus, let's see, which one do I want first? How about 1 plus I over h bar Hamiltonian times epsilon plus corrections of order epsilon squared acting on omega naught. And then on the right-hand side, again, I have identity operator now minus I over h bar Hamiltonian times epsilon plus corrections of order epsilon squared. Within this accuracy, I can exponentiate both of these things and say this is e to the plus I over h bar Hamiltonian times epsilon plus small corrections. And on the other side, I have e to the minus I over h bar Hamiltonian times epsilon plus small corrections. This is actually a lot more useful. So I get omega of epsilon equals e to the I over h bar Hamiltonian times epsilon omega naught e to the minus I over h bar Hamiltonian times epsilon with corrections of order epsilon squared. And now again, the logic that we've built several times now continues to apply, that because the symmetry transformation is additive, if I time evolve it by epsilon 1 and then time evolve it by epsilon 2, I'm just going to get something that is additive in the arguments. And that exponential form automatically satisfies that multiplication rule. So the argument that worked for us before continues to work now. This is still the solution even for finite time translations. Omega of t is given by e to the I over h bar Hamiltonian times time, omega naught, e to the minus I over h bar Hamiltonian times time. Now exact. So this is the solution to Heisenberg's equations of motion. And if you wanted to, you could take this form and you could expand it out order by order in time and show that doing this completely recovers this terrible nested commutator structure that we started with, fully exponentiated. Okay, great. So in Heisenberg picture, an observable is a matrix element of this time-dependent operator in some states. So a physical measurement corresponds to a matrix element of the time-dependent operator omega hat of t. So if I want to describe, say, the transition probability from state I to state F as a function of time, I would take that operator and I would sandwich it between basis states. So let's just take I and j. In Heisenberg picture, the operator is the time-dependent part. And this is what gives me, let's say, omega ij as a function of time. And since we know what the solution for the time dependence of the operator is, this is just I e to the plus I over h bar Hamiltonian times time omega naught e to the minus I over h bar Hamiltonian times time ij. So this is the result that we get, but we see that we could reinterpret the answer if we wanted. This operator, acting on that basis state, could be reinterpreted to say that my state is time dependent. So I could call this quantity basis state j as a function of time is e to the minus I over h bar Hamiltonian times time acting on the state at t equals 0. So if I absorb these time-dependent factors into time-dependent quantum states, I of t here, then I can reinterpret the same measurement in a different way. So this is also equal to I of t times omega naught times j of t. So these are two different interpretations of the same measurements. Mathematics is completely identical, it's just a choice of perspective, similar to the discussion of active versus passive transformation. So this picture where the time dependence lives in the quantum states is referred to as the Schrodinger picture. That's the one that we're going to stick with for essentially the rest of the class. It's a bit more intuitive to think of a quantum state beginning at a certain level and then something happens to it causing it to transition to some different quantum state. But in Schrodinger picture, it's less obvious how the connection to classical mechanics comes in. So to summarize, in Heisenberg picture, we have omega ij of t is interpreted as I times omega of t, j. And when we plug in the formal solution, we get the same quantity. So in Heisenberg picture, the operators are time dependent. Operators are time dependent. And the quantum states are constant. In Schrodinger picture, the operators are constant. And the states are time dependent. So we would describe the same matrix element omega ij of t as I of t on omega naught, which is time independent, j of t. Again, recover the same mathematical expression. For emphasis here, let me call them I naught and j naught, since they are time independent. Okay, so we've already solved the quantum equation of motion in general in writing it in this form. So this information about this e to the minus I ht acting on the state must contain the time dependence described in the Schrodinger equation. And indeed it does. So in Schrodinger picture, time dependence of a quantum state is given by this exponential. If I have a quantum state psi as a function of time, I obtain it from the one at t equals 0 by letting e to the minus I h bar Hamiltonian times time act on the wave function psi at t equals 0. This operator is a unitary operator, u of t. And this is called the time evolution operator. In Schrodinger picture, this is the operator that performs the symmetry transformation, which is why time evolution is generated by the Hamiltonian, as guaranteed by Noether's theorem. The time evolution operator u of t equals e to the minus I over h bar Hamiltonian times time is the solution of the Schrodinger equation. In the same way that this exponential form here was the solution to Heisenberg's equation of motion, the single operator, unitary operator, which gives you the time dependence of the state, is the solution of the Schrodinger equation. And the finite transformation and the infinitesimal transformation contain the same amount of information. So if I take this exponential form and I just expand it for a small step in a time evolution, small step t goes to epsilon of time evolution, we can recast this as a differential equation. Solution to a differential equation. So if psi of t equals u of t psi naught, by which I mean e to the minus I over h bar Hamiltonian times time on psi naught. If I expand this to lowest order in its Taylor series, I get psi of epsilon equals psi naught minus I over h bar Hamiltonian times epsilon times psi, plus corrections of order epsilon squared. And now if I just subtract the constant term to the left, psi of epsilon minus psi naught, divide by epsilon minus I over h bar Hamiltonian acting on the quantum state psi naught. Now I can take the limit epsilon going to 0 to get a differential form. In this limit, the left-hand side is simply the time derivative. This is d dt psi of t equals minus I over h bar Hamiltonian acting on psi. And this is the time-dependent Schrodinger equation. The IH bar to the left-hand side, this is IH bar d dt psi of t equals Hamiltonian times psi of t. I will often abbreviate this as TDSE for the time-dependent Schrodinger equation. So these two formulations are completely equivalent. The exponential form given for the time evolution operator is the solution to this differential equation. That is completely equivalent to the quantized version of this solution from classical mechanics. So it was very important to me to show you that the Schrodinger equation comes from somewhere. It is reasonably motivated as an extension of classical physics and not some brand new postulate that you have to assume is handed to you by God. So how do I interpret what the Schrodinger equation is telling me? The time-dependent Schrodinger equation describes how a non-stationary state evolves in time. It also describes how a stationary state evolves in time, but those are trivial. So, for example, I can turn this into a differential equation by taking this vector expression in linear algebra and simply projecting it onto a coordinate basis. We can convert this to a regular partial differential equation by projecting onto a position basis. So if I start with the time-dependent Schrodinger equation and I hit it on the left with the position vector x, then on the left-hand side I have I h bar. I'm going to write this now as a partial derivative with respect to time. Psi of t projected onto x. There wasn't any x before, so this was a total time derivative of something that depended only on time. This quantity is, of course, the wave function psi of x and t, so it now knows about x for the first time. On the right-hand side, I get a matrix element of the Hamiltonian. So what is this expression? For this, in terms of an interpretation and making contact with what you've seen before in your undergrad classes, it's useful to describe the Hamiltonian for a single particle moving in a potential. Well, let's just take everything in one dimension now for simplicity. For a particle moving in a potential in one dimension, classically, we would say the Hamiltonian function is p squared over 2m plus some potential v of x. Quantum mechanically, I have to make this a Hamiltonian operator. This is a momentum operator squared, so there's two of them. Plus, now my potential becomes an operator. It is an operator function of operator variables. If that sounds weird or confusing, I don't mean anything complicated by it. I just mean that both of these functions are defined by their Taylor series. V of x equals some constant v naught plus a linear term v1 times x plus 1/2 v2 x squared plus yada, 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 the whole terms and set of terms in the Taylor series. This quantization procedure means that the function that I get is described by the same constants, but now the x's are operators. v2 x hat squared, and so on. So that's what I mean when I say v hat of x hat. So in this case, then, the matrix element that enters the time-dependent Schrodinger equation is projected on basis state x. The Hamiltonian is p squared over 2m plus v of x, acting on psi of t. So let's split these terms apart. pull out the constants at least. So the first one, I have 1 over 2m x. Let me write this as p times p psi of t plus x v hat of x hat psi of t. Now, working in the position basis is highly advantageous for describing a position-dependent potential, because every time I have one of these position operators, if it acts on a position eigenstate, then it just returns back the position x as a regular scalar variable. So what I'm saying is that this operator acting on that bra x is just the scalar function v of x times the same quantum state back. If it was acting on any other state that was not an eigenstated position, this would not be true. But this already gets us halfway there to obtaining the familiar differential equation form of the Schrodinger equation. P psi of t plus, this is now v of x, and after I use the fact that the position bra is an eigenstate of the potential, the matrix element that remains is just the wave function. This is psi of x and t. Now we've got to work a little bit harder here for the momentum operators, because these are not being taken in their own natural eigenbasis. We know, however, what the momentum operator does. We worked it out before for the case of just functions and translations. So recall that P is h bar k, and k acts on a quantum state in a position basis like a derivative, with x k psi equals minus I d dx x psi. So this is the origin of what is usually written as P with an arrow goes to minus I h bar d dx. Even so, there's still another subtlety here because I have two of them. I can't just trivially apply this fact to this matrix element. I have to work a little bit harder first. So for the sake of being careful and showing you how you have to work this out in general for a quantum problem, let's go through the exercise of inserting that complete set of states. So we've been evaluating the matrix element of the Hamiltonian on psi of t projected into the coordinate basis. And we got h bar squared over 2m x p, sorry, let me call this k since I've already pulled out h bar, k psi of t plus v of x psi of x and t. So to evaluate this operator using this fact, I need to insert a complete set of states in between. So I'm going to write this as equal to integral over a new set of positions. I'm going to call them y, x, k, y, y, k, psi of t. So now I can apply this fact. This quantity is minus I, derivative with respect to time, acting on y psi of t. And this is nothing more than minus I d dt times the wave function, psi of y and t. This one gives me similarly a derivative, but this is a derivative acting on the delta function. So this is going to give me minus I d dx. Sorry, I don't know why I wrote d dt. Sorry, this is d dy, excuse me. So minus I d dx acting on what's left over. But that thing is a delta function, minus I d dx delta of x minus y. So you could formally write this as a delta prime if you want. Delta prime is just shorthand for saying you're going to have to integrate by parts. So this expression is minus I squared integral dy d dx delta function of x minus y d dy psi of y and t. And you can integrate this by parts, but you can also do it a little bit more simply than that. Since nothing else in the expression depends on x, I can pull this derivative outside. This is minus I squared d dx integral dy delta function of x minus y dy psi of y and t. And then I just use the delta function to set y equal to x. Minus I squared d squared dx squared psi of x and t. So plugging all of this back in, I get, let me write it this way, 1 over 2n times minus I h bar d dx squared psi of x and t plus v of x psi of x and t. And so now this is going to give us the familiar differential equation form of Schrodinger's equation. Time-dependent Schrodinger equation is I h bar d dt psi of x and t equals 1 over 2m minus I h bar d dx squared psi of x and t plus v of x psi of x and t. And of course, we can just pull this out and write it as a differential operator minus h bar squared over 2m d squared dx squared plus v of x times psi of x and t. So again, this is the time-dependent Schrodinger equation, but now written in a coordinate basis for a 1D particle in a potential. Now, this quantity in brackets is a differential operator that is essentially the Hamiltonian. Sometimes you'll see this written as h hat. But be careful, that is a different thing than what we've been calling it thus far. But this is a differential operator involving derivatives. Acting on the wave function not the thing that we've been calling h, which acts on a quantum state psi. It's almost as good, but it's not as general. One thing to emphasize about this is that this differential equation formulation, right? So sometimes written as I h bar d dt psi equals h psi. This h is the differential operator. This is just one possible representation of the Schrodinger equation. And that's very clear in this algebraic setup because the basic equation is formulated at the level of the state vector. And the position basis is just one of an infinite number of choices that you could make that might be more or less useful to you depending on the problem. So alternatively, you can equally well express Schrodinger's equation in the momentum basis or the plane wave basis. Called it before the plane wave basis. And since momentum is just proportional to wave number, this is the momentum basis as well. if I take the Schrodinger equation, IH bar d dt psi of t, and project it equals h psi of t, and project it now onto a momentum eigenstate p, I get IH bar partial derivative with respect to time of the overlap of psi of t with the momentum state p. So this is a different kind of wave function. This is psi of p and t. Momentum space wave function. But there was never anything particularly special about position. On the right-hand side, the price that I pay is that now I'm taking the matrix element of the Hamiltonian projected onto the momentum state, P. If I have a single particle in one dimension in a potential, then this is P operator squared over 2m plus V operator as a function of X operator, psi of t. Now the kinetic energy is the simple part. The piece that became a derivative in position basis is now just a simple eigenfunction in momentum basis. So this is p squared over 2m times psi of p and t, plus now the hard part is describing the potential, v of x, psi of t. I won't go through the general Taylor series insertion of complete sets of states everywhere, but the exercise is basically the same thing that we did here for the momentum operator derivative basis. At the end of the day, what we get instead is a differential operator v whose argument x has now been replaced by a derivative operator, right? So this is now plus I d p h bar somewhere, IH bar ddp, acting on psi of p and t. And again, this differential operator is defined by its Taylor series. You have a constant, a linear term in the derivative, a second order term, and so on. So you can perfectly well write down the Schrodinger equation in the momentum basis instead of the coordinate basis. And then you get IH bar d dt psi of p and t equals now just a scalar quantity, p squared over 2m plus a differential operator for the potential, IH bar d dp, and on psi of p and t. So this is the time-dependent Schrodinger equation in momentum space. And again, this is for a 1D particle in a potential. Usually the potential is the complicated part and the kinetic energy is the easier part. So it is usually more advantageous to try to solve this differential equation in position space. But again, there's nothing God-given about position space. So I wanted to emphasize that this is only one of many possible representations of the Schrodinger equation, and it stops working well when you're not just describing continuous functions. It doesn't work very well when you have to incorporate something like spin. The PDE formulation is not fully general. It is, especially the coordinate space representation, is only one formulation among many. Just corresponds to a choice of basis. Doesn't work very well with things like spin. But all of those features are still nicely captured within the linear algebra framework. So that was the time-dependent Schrodinger equation for a general quantum state that is usually not a stationary state. Now let's discuss the special case when you have something that is an eigenstate of the Hamiltonian. So I will write Hamiltonian acting on the particular state E and T gives me back the energy E times the same state again. Normally, the time dependence is not written explicitly for a state like this, but we want to work out now what that time dependence is. So this eigenvalue equation is essentially the time-independent Schrodinger equation. Psi equals E psi. But the Hamiltonian does predict that there is some time dependence for the state. One can work it out by solving the differential equation, but we've already solved the differential equation in operator form, so it's faster just to plug it in. The time dependence is given by the time evolution operator, U of t, acting on the same state starting from t is equal to 0. This is e to the minus I over h bar, Hamiltonian times time acting on the quantum state, e, t equals 0. But since this state is an eigenstate of the Hamiltonian, every time the Hamiltonian acts on it, it generates a factor of E. So if you want, you could think of expanding this thing in terms of its Taylor series. Every time you have H, E, replace it with E, E, and then you sum it all back up into a Taylor series at the end. Or in general, this is just saying every time you see H, it gets replaced by E when acting on this particular quantum state. So we get e to the minus I over h bar energy times time. E t 0. This is the time dependence of a stationary state. Or if I project this onto a position basis, x e and t equals e to the minus I over h bar, e and t x e and t equals 0. This is just giving me the wave function psi of x and t equals e to the minus I over h bar, e times t, times psi of x and t equals 0. So the wave function is a complex function. The time dependence is completely encapsulated in this time-dependent phase. So the complex phase is changing as a function of time. The magnitude of the complex number is not. Rotating in time. So in terms of the complex plane, you might think I have the real axis of some complex number, the imaginary axis of some complex number. This is describing a point that starts out with some fixed magnitude and then moves in a circle. Its complex phase, which is describing this angle, theta. Theta is the complex argument of z. This thing is rotating as a function of time, but the magnitude, the distance from the origin, is always the same. Complex phase is rotating in time, but the magnitude is stationary. I want to try and sketch what this might look like for an actual wave function, but please bear with me. I am not an artist for a reason. So now in the plane going into the page, I want to show the real part of the wave function and the imaginary part of the wave function, and I want space to be along the x-axis here. So if at t equals 0, I have some wave that looks like this, then as a function of time, that wave is changing. It's changing because it's rotating like a jump rope in that plane going into the page. So as a function of time, this point up here moves in a circle in that complex plane. This point here moves in a smaller circle in that complex plane. This point here is stationary. Its magnitude is 0, so it doesn't change at all. And so on. So the picture I have in my head is like two kids spinning a jump rope. The wave function itself has a it has a time dependence. I guess it's a trivial time dependence. But the wave function squared is completely stationary. If I do psi squared versus x, the point where it's 0 is still going to be 0, and I guess it just kind of falls steeply like this. And recall that the wave function squared, or the wave intensity, is the actual probability density. So the probability distribution is stationary in time. So that doesn't mean that the state is completely time independent. It just means that the time dependence is trivial. It's just that complex phase rotation. The probability density is stationary. That doesn't mean that the phase information is not physical or not important. That has everything to do with how waves superimpose with each other. But if you solved for the equation of the system and it's just sitting there stationary and rotating in complex phase, that doesn't change the probability of measuring the particle in a certain state as a function of time. Okay, fantastic. The last thing that I wanted to write down is a simple expansion of the time evolution operator now in terms of the eigenbasis of the Hamiltonian. It's another simple way of writing down the time dependence. Energy eigenbasis. We said the time evolution operator U is e to the minus I over h bar Hamiltonian times time. If I insert a set of complete states, I'm going to do it twice. I'll choose a sum over the complete set of energy eigenstates. So I will insert completeness to the left and to the right. The advantage of this is that now in the middle, I've sandwiched a matrix element of the Hamiltonian, essentially, between its own natural eigenstates. So here, since the Hamiltonian is acting on the state E, I just simply get back the state E again, and this is now just the scalar quantity I over h bar energy times time. Not only that, this is now projected onto a different energy eigenstate E prime, and this thing just gives me the Kronecker delta. These must be the same eigenstate. And then when I sum over the Kronecker delta, I kill one of the summations. I set E prime equal to E, and I just get sum over energy eigenstates, E to the minus I over H bar, energy times time, E, E. So I think it's useful to deconstruct what each piece of this expression is doing. This is a projection operator. Much like the building block when we did Gram-Schmidt orthogonalization. You take whatever quantum state you have, you take its overlap with a particular energy state, and then you point it in that direction again. Once I've projected onto a specific energy state, I know what the time dependence is. So this is pure phase rotation. And that speed of the phase rotation depends on what that energy is. With speed or frequency, omega equals E over H bar. And now I have a complete sum over all possible energy states. Over the different modes that have different energies. So my picture is again similar. My picture is again similar to this jump rope. So if this is the picture of the time dependence of one mode, that it's just pure phase rotation, then this decomposition is a way of saying any wave function can be written as a superposition of different energy eigenstates. Each one is a spinning jump rope, and each one is spinning with its own frequency. So by summing all of those effects up, you accumulate the total impact on the wave function. Say the total interference pattern, i.e. the wave function of those spinning jump ropes. Okay, fantastic. That was everything that I had wanted to cover today. I guess the last comment that I'll leave you with is that we already know that all of this discussion about time evolution is much, much more general than just time. That all of this discussion, starting from quantization of the Poisson bracket here, this applies for any symmetry transformation. The Hamiltonian generating time evolution, the momentum operator generating coordinate translations, angular momentum generating rotations. It doesn't matter. Because the algebra always works in the same way, the structure of the quantum evolution is also always going to be the same. So you will always have something of the form where it looks like unitary operator on the right side, opposite unitary operator on the left side. And when you translate that into a Schrodinger picture action on a quantum state, the unitary operator U that is going to generate any symmetry transformation on that quantum state is going to be written as E to the minus I over H bar, the generator, whatever that is, times the coordinate, the amount of that translation. And this whole discussion was just the special case of the Hamiltonian generating time evolution. All right, fantastic. What questions do you have? Okay, if there are none, then thank you for your time, and we will pick this up on Tuesday.
Thank you.
Thanks very much, guys.
Thanks.